Okay, welcome back to GLS4OM. Still continuing our work on Unit 7, which was Techniques of Integration. Today we're going to be looking at improper integrals and how we might use some of the techniques that we've seen so far to evaluate them. So as per practice, we're going to start with a little humor of the day. The laptop is saying, I can't get it off. And the monitor replies, dude, that's because your caps lock is on. All right, so what's an improper integral? So the definition of a definite integral we know is this, the integral from a to b. It requires that the function is bounded on a, b. So a and b are real numbers, and there has to be a bound because we're trying to give a numeric answer back for this, which would be the area bounded by the curve in between a and b. Everything we looked at so far was a bounded regions. Sometimes unbounded regions arise, and they are represented by what we would call an improper integral. We've got a definite integral that is could be unbounded. Those are called improper integrals. Now, an integral can be improper. One of two ways it can happen. One is the interval is unbounded, so we're going to make the bounds of integration either positive or negative infinity, one or more or both of them. When you do that, that's called an improper integral. It might also be an improper integral because it might not be bounded on AB, which means you've got a vertical asymptote happening in there. So if there's a vertical asymptote happening in there, then the integrand might tend to infinity. It might not. So how could an unbounded region have a finite area? That's what I'm going to get you to think about now. So the integral from negative infinity to c, would that be finite? Would the integral from c to infinity be finite? What about the integral from negative infinity to infinity of a function? Would it be finite? So currently what I'm looking at right now is the integral we're looking at from c to infinity. And currently in this Desmo sketch I have here, we're starting at 0. All right, so we're starting at the left end of 0 and we're heading out to c. So what happens if I send c off to infinity and you're looking at the area under the curve? Do you see how the additional area that's being added is so very tiny that it's likely this is being bounded because that extra area is approaching 0, sort of similar to the Koch snowflake idea where the additional area you were adding was so small that you ended up having a region with a finite area. So let's take a look at this numerically. I'll wait for this to pop back up again. I want to show you the function we were looking at. So the function we're looking at was, this is e to the negative x. I forgot to tell you that. We're looking at e to the negative x. So coming over here. So we're looking at, if it was a definite integral, we're looking at the integral from 0 to c of e to the negative x. That shouldn't be that hard to do because we can take the antiderivative. The antiderivative of e to the negative x is negative e to the negative x. And evaluating across our bounds of integration 0 to c, that would give us negative e to the negative c minus negative e to the 0. And of course e to the 0 is 1. And a negative times a negative is a positive, so that becomes 1. And this will be 1 minus e to the negative c. So if we are going to now send c to infinity, because that's how I'm going to look at this now, instead of looking at this as the integral from 0 to infinity of e to the negative x dx, I'm going to look at it as the limit as c goes to infinity of the integral from 0 to c of e to the negative x dx. That would become the limit as c goes to infinity of, we just evaluated this up here, 1 minus e to the negative c. And as c goes to infinity, the e to the negative c will tend to 0. This will be 1 minus 0, which is 1. So the area under the curve, let's take a look at this here. The area under this curve, hopefully it doesn't take too long for this to pop back up. So the area under the curve, drop the pencil, from here, 0 all the way out to infinity, believe it or not, that is 1. Let's drag that out. So that green area heading all the way out to infinity, the area between e to the negative x and the x-axis from 0 to infinity is exactly 1 unit, and we demonstrated that right here. So, technique number 1 for an improper integral. So if it's the integral from a to infinity of f at x dx, you can rewrite it as the limit as c goes to infinity of the definite integral from a to c of f at x dx. You can then evaluate this and then do the limit afterwards. If it converges, the limit exists, and it would be a finite number. If it diverges, then the limit doesn't exist because you're heading off to positive or negative infinity. Similarly, if it was the integral from negative infinity to a, we can now do the limit as c goes to negative infinity, and now we'll make the lower bound of integration c. We'll leave the upper bound of integration alone. Note here, we left the lower bound of integration alone because it was a finite number, and we've changed the infinity to a c. What happens if we're going from negative infinity to infinity? That's not a problem because there's a property of integrals that allows us to split this way. We'll split at 0, the integral from negative infinity to 0 of f at x dx, plus the integral from 0 to infinity of f at x dx. And then applying these techniques we looked up there, this will now be the limit as c goes to negative infinity, integrate from 0 to infinity on it, plus the limit, or from c to 0, plus the limit as c goes to infinity, and integrate from 0 to c. So then I will show you an example of how this would work, and then you'll try one. So if we're trying to evaluate the integral from negative infinity of x e to the negative x squared dx. So this is unbounded. It's an improper integral because our bounds of integration, one or more of them, is infinity. So I'm going to split this into two bounds, the integral from negative infinity to 0 of x e to the negative x squared dx, plus the integral from 0 to infinity of x e to the negative x squared dx. And using the technique we just learned, what I'm going to do now is replace this with the variable c. So I'm going to integrate from c to 0, that definite integral, and then I'll evaluate the limit as c goes to negative infinity. And on this side, I'm going to integrate from 0, make this the variable c, and then I'm going to look at the limit as c goes to infinity on my function, which is x e to the negative x squared. Now, the antiderivative of x e to the negative x squared is negative 1/2 e to the negative x squared. And you could figure that out on your own. I'll get you to do that, but you could just do the substitution u equals negative x squared. So if you do that substitution on there, then you can go backwards and integrate that. The purpose of this lesson now is moving forward and using previous techniques that we learned. We're now going to be focusing on evaluating improper integrals. And if you wanted to differentiate this, you would get e to the negative x squared times the derivative of the baby, which is negative 2x. And negative 2x times negative 1/2 is x. So you can see that we are indeed getting back to where we need to be. So now we have the antiderivative of this. We now integrate this one from c to 0. And this one we're going to evaluate from 0 to c. I said integrate, but I meant evaluate along the bounds of integration. So plugging in the upper bound here, e to the 0 is 1, so we're going to get negative 1/2. Then we will plug in the c, but we're going to take that away. So minus a negative becomes a plus here. And plugging in the c, we get 1/2 e to the negative c squared. Taking a look at this one, we're going to plug in the upper bound first, and we're going to get negative 1/2 e to the negative c squared. Take away the lower bound, taking away a negative becomes plus. And when you plug in a 0 here, e to the 0 is 1, so we're going to get plus 1/2. And now we're going to send c to infinity. So this is e to the negative c squared. If you square negative infinity, you will get positive infinity. And e to the negative positive infinity is e to the negative infinity. And that, of course, is just going to become 0. That's how that becomes 0. When we plug in infinity here and square it, we get infinity, and e to the negative infinity is 0, so this piece becomes 0. So I now have negative 1/2 plus 0, minus 0 plus 1/2, and all of that becomes 0. Now, if you have time, you should take a look at the graph of this curve, because it looks like there's symmetry. The area from negative infinity to 0 is negative 1/2, so that area is below the curve. and this, or is below the x-axis, I meant to say, and this area is above the x-axis. So it sounds like this is probably an odd function. There should be some symmetry about the origin. The area below the axes is canceling out the area above. So it's not that there is no area altogether, it's just that there's an equal amount of positive area and negative area. All right, so moving forward. You're going to try that technique. Let's try it on this one first. So you saw how that technique worked. We're going to change this into a limit. We're going to change the bound of integration that's infinity to our variable, and then we'll do a limit as our variable goes to infinity, and then we'll change this to a definite integral, which we will evaluate. And it is time for our first time to ponder pause. All right, so taking this up, we're going to replace this with a c. So I'm going to look at the definite integral from 2 to c of dx over x cubed. And then I'm going to look at the limit as c goes to infinity in front of that. Like, it's a nifty little technique. These will evaluate to the same thing. This we can't do anything with, but this we can evaluate because we can work through this definite integral. So the antiderivative of x to the negative 3 is negative 1/2 x to the negative 2, which I've chosen to write as negative 1 over 2x squared. I now need to evaluate along the bounds of integration from 2 to c. We'll start by plugging in the upper bound. We will get negative 1 over 2c squared minus, this time I wrote them in, minus 1 over, we're going to plug in the 2, so 2 times 2 squared, that becomes 4 times 2 is 8. Negative times a negative is a positive, that becomes plus 1 over 8. So we're going to look at the limit as c goes to infinity of negative 1 over 2c squared. When c is infinity, this becomes 1 over infinity, which is just 0. We're now going to have 0 plus 1/8, and that is going to evaluate to 1/8. So this integral, this improper integral, using the technique I've shown you here, we can figure out that that evaluates to 1/8. So the area under the curve from 2 to infinity is 1/8. And we would say this particular interval is converging because it converged to a finite value. All right, same technique you're going to apply to that one. And again, it's the second time to ponder pause. And resuming. Now it's the lower bound of integration, that's the infinity, so we're going to replace that with the variable c. We're going to look at the integral from c to negative 1. We're now going to have our limit being as c goes to negative infinity. We now have dx over x. The antiderivative of dx over x is the ln of x, and now we're going to evaluate that across our bounds of integration from c to negative 1. We are going to have to start now. Do remember that we do have to put absolute value around this. Because the only restriction on the original function here is x can't be 0. It can be negative numbers. You don't put the absolute value around here, you're not going to be able to plug in the negative number. And look what we were trying to plug in. It was a negative number. So evaluating across our upper bound of integration, it's the ln of the absolute value of negative 1 minus evaluating on our lower bound of integration would be the ln of the absolute value of c. The ln of the absolute value of negative 1 would be 0. That would become the ln of 1, which is just 0, minus the ln of the absolute value of c. I still need the absolute values over here. I'm now going to plug in my negative infinity, and I'm going to get 0 minus the ln of the absolute value of negative infinity, and that's just going to become the ln of infinity. And of course, the ln of infinity is infinity, and I'm just going to pause for a sec. All right. I just have to take care of the phone situation there. All right, we're good to continue. So, forgot where I was. I'm just going to repeat myself then. Oh, no, I remember where we were. We're talking about the ln of the absolute value of negative infinity becomes the ln of infinity. The ln of infinity is infinity, but I do have that minus out in front. So this evaluates to negative infinity. So this is equal to negative infinity. This one was equal to 1/8. So an interesting technique that allows us to evaluate these improper integrals when our bounds of integration are unbounded. In this particular integral, we would say diverges because it's heading off to an infinity. This one's converging because it's heading to 1/8. All right, so now I've shown you how to handle it when the bounds of integrations are infinity. What are we going to do jumping too far forward? Let me just pause for a sec. All right, I did jump too far forward. What I want to do next is what happens when you encounter a vertical asymptote. So we did say at the very beginning of this lesson, which was here, there are two ways an integral can be improper. We had just done the case where the interval is unbounded. We looked at both a being infinity, in fact a being negative infinity, and b being positive infinity. And now we're going to take a look at what happens if you encounter a vertical asymptote. So even though we are bounded here by finite values, what happens when there's a vertical asymptote? So that's jumping to this slide. So what we're going to do now is we're closed on this end A, but we're open on the B. So the vertical asymptote is likely occurring at the B here. So now we're going to change this to the limit as we're going to go from A to C, but C is going to be B negatively, right? We can't cross over B to the other side. So here is A. And here is B. And we have some kind of asymptote heading here. So as long as we approach B negatively, we will not have crossed over the vertical asymptote. So we're going to look at the limit as C goes to B negatively of the integral from A to C. We've replaced this with the C of f at x dx. And what happens if we're doing it on the lower bound? So this was the vertical asymptote occurring on the upper bound, right there. The vertical asymptote is going to occur on the lower bound. So what we're going to do is we're going to replace this with C, but now we're going to head to A positively, because again, here's A, here's B. We've got a vertical asymptote here. We don't want to cross the vertical asymptote on the left-hand side, so we're going to approach A positively. When the vertical asymptote is at B, we don't want to cross the vertical asymptote, so we will approach B negatively. And then I'll walk you through an example. And we're going to look at the integral from 0 to 2 of 3 over x squared. Now, the vertical asymptote is occurring right here. We would be dividing by 0 if we let x be 0. We don't want to cross the vertical asymptote, so we're going to be approaching 0 positively. So the limit as C goes to 0 positively. We're going to integrate from C to 2 now. The antiderivative of 3 over x squared is negative 3 over x. And again, I have been doing it this way, but in this case I put them in square brackets. That's another accepted form, except when you do that, someone might have initially thought that that was an exponent. It's not an exponent, it's the bounds of integration. So maybe it's better to do it this way. So we're now going to evaluate across our bounds of integration C to 2. So plugging in our 2, we get negative 3 halves. Take away a negative becomes plus, and then we're going to plug in our C, so we get 3 over C. So we're negative 3 halves plus 3 over C. And then we're going to send C to 0 positively. We're going to be looking at that 3 over 0 positively. I think we've seen that enough times that we recognize that 3 over 0 positively is just positive infinity. So this is now going to evaluate to negative 3 halves plus infinity, which is infinity. So this particular integral is diverging. All right, I'm just going to pause for a sec. All right, ready to resume. I could see that on the next slide when it was coming up, I could see that I had the answers pasted on it. I didn't have the blank slide. I really would prefer to give you a chance to think. So we're going to come to these ones here. Determine if the following integrals converge. And notice the bounds of integration here are finite. The issue with this particular one is we are approaching our vertical asymptotes on our ends. So how about you set this one up first? And I believe this is our third time to ponder pause. All right, so taking this one up, the vertical asymptote is going to occur on the lower bound. It's very similar to the one I just did. So we're going to approach 0 positively. I don't want to cross the other side of that vertical asymptote. It's on the left edge. There's 0, 16 is over here. So we don't want to hit 0 negatively. If we do, we'll be crossing the vertical asymptote. So I'm looking at the limit as c goes to 0 positively of the integral from c to 16 of 2 dx over the fourth root of x. If we want to go backwards on this one, this was x to the negative 1/4. We would have 2x to the exponent negative 1/4 plus 1, all divided by negative 1/4 plus 1. This is going to give you 3/4. And if you divide by 3/4, you'll get 8/3. So now we have the integral of 8/3. I really have no idea where this negative here has come from. I'm just going to change that into a plus because that should not be a negative. There's no negative here, so there shouldn't be a negative there. All right, and again, I was saying if you divide by 3/4, that's multiplying by 4/3. 4/3 times 2 gives you your 8/3. So now the antiderivative of this has become 8/3 x to the 3/4. Evaluating across our bounds of integration, plugging in the 16 first, 8/3 times 16 to the 3/4 minus 8/3 times c to the 3/4. The fourth root of 16 is 2, and 2 cubed is 8, and 8 times 8 is 64. So we get 64 over 3 minus 8/3 times c to the 3/4. We've simplified as far as we can, and now we will evaluate the limit. So we've simplified the definite integral, evaluating the limit, sending c to 0. When we plug a 0 in here, this piece here, that whole entire piece is just going to become 0. 64 over 3 minus 0 is 64 over 3. So this particular integral, it's an improper integral, this converges to 64 over 3. All right, let's see if you can apply the same technique to this one. And this is our fourth time to ponder pause. All right, so resuming, we can see now that the vertical asymptote is going to occur when x is 3, so it's occurring off the upper bound. So we should be approaching 3 from the left. In this case, we're approaching 0 from the right. So we're going to take a look at this. I am now going to be setting up the limit as c goes to 3 negatively. I don't want to cross over that vertical asymptote on the right. I want to stay to the left of 3. So we will integrate from negative 1 to c of 2x dx over the square root of 9 minus x squared. Now the antiderivative of this is negative 2 times the square root of 9 minus x squared. That's the antiderivative. I don't want to belabor these things and make them much longer because we had already practiced this before. If you want to evaluate this integral, you can simply do a substitution. Look at the derivative of the baby is sitting right there. So let u be 9 minus x squared, and then du would be 2x dx, and this is just going to become the integral of du. Actually, we've got a negative as well. So I did say 2x dx is negative 2x dx. So we're going to be negative du over root u. And that's how I got to there. All right. Now moving forward. That should be c negatively. I'm now going to evaluate my definite integral across the bounds of integration. I will start by plugging in my c. So I get negative 2 times the square root of 9 minus c squared. Taking away my lower bound is negative 1, so I'm going to plug a negative 1 in here. So negative 2 times the square root of 9 minus negative 1 all squared. Negative 1 all squared is 1, and 9 minus 1 is 8. That should be plus. I got an extra. Let's just cross that off. Multiply a negative by a negative is plus. So this is going to become plus 2 times the square root of 8. So I have my negative 2 times the square root of 9 minus c squared. I'm now ready. I've simplified it as far as I can. In fact, you really can't clean up the part that has the variable. It's the numeric part that you want to clean up. This cleans up to 2 root 8. And now I'm ready to plug 3 in. It is 3 negatively, but we can see if we plug 3 in here, we're going to get closer to 3. This is just going to keep getting closer to 0. And remember, we've set it up so that we're just going to stay smaller than this. So this will be defined. This will never become the square root of negative. So this is 0 positively. Negative 2 times 0 is 0, and 0 plus 2 root 8 is 2 root 8. So this one converges as well. It converges to 2 root 8. All right. Now let's move forward to what's known as a P integral. So convergence of these improper integrals. And we're backing up, we're thinking about, we're dividing by x to the p. So it's an improper integral of a power function. And the power function we're looking at is x to the negative p. It's called a p integral. And the exponent p equals 1 ends up being the dividing point between convergence and divergence. So if we have the integral from a to infinity of dx over x to the p, and p is greater than 1, this one will converge, but the integral from 0 to a will diverge. Again, same function. We're just splitting it at a. We're looking from 0 to a, and we're looking from a to infinity. When p is less than 1, then this part diverges. The a to infinity part diverges, and the part from 0 to a converges. And when p is 1, then both of these diverge. And so I'm just going to sort of show you in this little Desmos bit. Whoops, let me pause to just fix that for a second. All right, several technical issues happening during this recording. So internet went down, and that's why the page disappeared. I was able to set up a hotspot with my phone so I can finish off the recording. So we were talking about convergence and this improper integral of this power function x to the negative p, which I have right here. And we were talking about that when p is less than 1, p is smaller than 1 right now. And we said that when p is smaller than 1, just going to show you back to the slide again. When p is smaller than 1, this bit will diverge, and the bit between 0 and a will converge. So let's take a look at that. Hopefully this doesn't take too long to load back up. All right, so p is less than 1. And take a look at this area right here that I'm looking at. See how small that is right there? So it's believable that that is converging. And then as we increase p, that's starting to get larger, right? Right there, we're at 1, and at 1, it's diverging. And now it's continuing to diverge. See how big that area is getting? And you can see how that's shooting off to infinity up there. Let's just zoom out a little bit like that. Maybe a bit like that. And then when we come back in here, that's getting smaller, smaller, and eventually it's small enough that when we get to here, we're converging. So right now what's happening, let's zoom in a bit. The area to the left is converging, and this little bit to the right from heading out to infinity, that part, so my A currently is a C. It's currently at 4.1. So the area from 0 to 4.1 is converging, but the area from 4 out to infinity is diverging. But if I allow P to be greater than 1, then we're getting the opposite situation. Let's zoom in a little bit here. We're getting the area from 0 to 4 diverging, and the area from 4 to infinity is converging. So that's what this is telling you here, the improper integral of P integrals. It's telling you when to expect convergence and when to expect divergence, and it all depends upon the value of P, and I tried to illustrate that for you right here on this little Desmos sketch. All right, just one more theorem to cover in this particular lesson. Comparing integrals. It might be desirable to determine if an improper integral converges even if we cannot find its exact value. You might even want to know whether an improper integral diverges. So there's something that's called the comparison test for improper integrals. And it says if f at x is greater than g at x for all x on a. So let's take a look at this, greater than or equal to a. So here's a. There's f at x, and you can see f at x is above g at x on that whole entire interval from a to b. Or actually, I guess from a to infinity, because if that's continuing, let's presume this is not getting steeper. I'm just going to back that way, so that it will always stay lower than f at x. All right, so what this is saying is if this one converges, i.e. if the area between this curve and the x-axis heading out to infinity converges is a finite value, then it makes sense that g at x would also converge because g at x is below it. That makes sense. If f converges, then g has to converge. And this one here says sort of the opposite of that. It says if the area between g at x and the curve is diverging, and the x-axis, sorry, the curve g at x and the x-axis, if that diverges for g, it must also diverge for f because f is above g. Now, if g converges, that doesn't mean that f is going to converge. And if f diverges, it doesn't mean that g has to diverge because it was lower. So the conclusion we can make is that if f converges, everything below f also converges. If g diverges, then everything above g would also diverge. All right, I'm going to show you that theorem in action. So if they asked me to show that the integral from 1 to infinity of e to the negative x over x converges, that's a tough integral to work with, right? You're going to have a hard time going backwards and trying to find an antiderivative on this one. But I do know that if x is greater than or equal to 1, because that's the bounds of integration, they said to be greater than or equal to 1, that e to the negative x over x is definitely smaller than e to the negative x. I want you to think that through. So you're dividing this value by a value larger than 1, then you're making it smaller. So e to the x exceeds e to the negative x over x. The integral from 1 to infinity of e to the negative x converges to e to the negative 1. And I'm just going to quickly take you back to slide 3. I believe it was somewhere around slide 3. It was somewhere in the beginning. Maybe it's slide 4. So we were looking at the integral from 0 to c, but if we do the integral from 1 to c over here, changing this to a 1, changing that to a 1, that will be negative 1. So I'm going to plug in my upper bound of integration would still be negative e to the negative c. But if my lower bound of integration is 1, then I'm going to get take away a negative, which becomes plus, and then I'm going to be looking at e to the negative 1. And then if we send c to infinity, this piece is going to go to 0, and then I'm going to be left with my e to the negative 1. So using, I guess this is slide 4 now, taking a look at slide 4, we can see that the integral from 1 to infinity of e to the negative x is e to the negative 1. So jumping back to our last slide, I just want you to know where that value came from. I just didn't pull it out of a hat, went back to slide 4 to figure that one out. So this diverges to e to the negative 1. So the comparison test would say this. 0 is less than or equal to the integral from 1 to infinity of e to the negative x over x dx, which is less than or equal to the integral from 1 to infinity of e to the negative x. We've just demonstrated that this one converges, so the comparison theorem guarantees that that one will also converge. All right, so that ends today's lesson, and today's lesson was all about thinking about improper integrals. It's a success for you if you are ready to handle an integral where we've got negative infinity and maybe ending at an infinity of something here, and then you're able to rewrite that as a limit. Or if we have the integral from a to b, but we had a vertical asymptote at b. Round bracket there, square bracket here. Or we're looking at the integral from a to b, where we have the round bracket at a and the square bracket at b, because you can rewrite that as a limit. And then the only other things we added there were this notion of what's a p integral. So if you've made it to the end of this lesson, awesome. Thanks for your support. I guess I will see you when we do lesson 7. I forget what lesson 7 is about, but I believe that is the last lesson of the unit. And then we'll be finished techniques of integration and we'll move on to unit 8. So once again, thank you for watching. Don't forget to like and subscribe. Feel free to contact me if you have any questions. And as always, take care and stay safe.